Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. I'm Dr. Owusu, and in today's session, we're going to be looking at the Unified Chemistry paper from 2018, and I will be picking up from where Miss Batten left off. In other words, we'll be looking at questions 4, 5, and 6 of that Unified paper. Now, of course, as the name suggests, it is a synoptic paper, and it really tests your ability to bring together disparate parts of chemistry using all the knowledge you've acquired on different topics and bringing them to bear on solving problems. And so over the course of today's session, I will be picking out some points of exam technique that will help you do this even more efficiently. Okay, so as usual, I will be connecting my tablet to your screens very shortly. And at various points during the session, I will be checking for any questions that you've got, and I will do my best to answer these for you. Do use the chat box and do type in any questions you've got on whatever I say, and I will pause to deal with those for you. Okay, so this session should last a little under an hour. We're looking at 3 questions, so approximately 15 to 20 minutes on each of those questions. We do have time to look at some of the detail of those questions. So do use the chat box if you've got any questions. I can't emphasize that enough. Okay, so if you give me a few seconds, I will connect my tablet and we'll be off shortly. Okay, so hopefully you can all see on your screens now the first question we're going to be looking at, which is from the 2018 Unified Chemistry paper. I will make that a bit bigger. Okay, so as I said, this is a synoptic paper, and we're looking at topics from all across A-level chemistry from the first and second years. And the first question looks at some transition metal chemistry, and we're looking at cisplatin specifically. And in this question, we're told that it is a complex of platinum which is used in cancer treatment. And the first thing we're asked is to say what the oxidation number of platinum is in cisplatin. So a bit of redox chemistry here. The first thing you want to do is to look at the overall formula for cisplatin, which I will highlight here. Okay, so that cisplatin, it's got no overall charge. Okay, so what we then want to look at next is the charges on the ligands attached to or bonded to the platinum. Now, if we look at the ammonia, there are 2 ammonia ligands. Each of those ammonia ligands is neutral. And then we've got 2 chloride ligands. Each of those chloride ligands has got a charge of -1. Okay, so the total number of minus charges is 2, -2 altogether. But there's no overall charge. And that must therefore mean that the platinum has got a charge of +2. So that +2 cancels out the 2 minus from the 2 chloride ions. Okay, so our first answer is +2. So platinum is in the +2 oxidation state. Again, there's no overall charge on your cisplatin. You've got chloride ions, each of which are 1 minus, so 2 minus altogether. The ammonia ligands are neutral, and therefore to cancel out the minuses of your chlorides, you need 2 plus. Okay, so that's our oxidation state for platinum dealt with. So 1 mark there. Hopefully that was pretty straightforward. Then moving on, we're told that cisplatin is prepared in a ligand substitution reaction, which takes place in multiple steps. And the equation for the final step forming cisplatin is shown below. So you've got your platinum complex, but it is complex to 3 chloride ions and 1 ammonia ligand. And the overall charge, as we would expect, is 1 minus. So this is the species we're looking at. And that is going to react with an ammonia molecule to give you the final product, cisplatin. And that ammonia molecule is going to replace your chloride ion. So your chloride ion is your sort of byproduct of this substitution. It says in the box, you need to outline the mechanism for the formation of cisplatin from your platinum complex, which has got 3 chloride ions, and so your trichloro and 1 ammonia ligand platinum complex. So use curly arrows and lone pairs where appropriate. Okay, so the first thing we want to do is to draw the structure of our platinum complex. So if we draw that, you've got platinum, and it's got 3 chlorine or chloride ligands, I should say, currently. So 3 chloride ligands, and it's got an ammonia ligand. And remember that it is charged. It's got a charge of 1- due to the number of chloride ligands we've got. And then it's going to be reacting with an ammonia molecule. So if we draw our ammonia molecule as shown, and a lone pair on that ammonia molecule, remember the ligand is going to form a dative covalent bond to the transition metal ion, in this case platinum. So a curly arrow drawn from the lone pair of the nitrogen of your ammonia and ending up at the platinum. And as a result of that bond being formed, or the lone pair from ammonia being donated to the platinum, you're going to break one of your platinum chlorine bonds. Okay, so you need to show that with a curly arrow from the middle of the platinum chlorine bond, ending up at your chlorine, your chlorine species, or your chloride, soon to be chloride. Okay, so as far as the mechanism goes, it's a substitution mechanism, a nucleophilic substitution mechanism, something you've come across in a different context, perhaps with halogenoalkanes, for instance. So curly arrow from lone pair of ammonia, which is your nucleophile, attacks the platinum and causes the platinum chlorine bond to break to give you your chloride byproduct and your cisplatin, of course. Okay, so that is part 2 dealt with, and you've got hopefully 2 marks there. We will look at the mark scheme very shortly to compare our answers to that. Okay, so we now have part B of this same question, and in part B we're shown a molecule or the structure of paracetamol, and this molecule has got a number of functional groups. We're told it is a painkiller, and the first part of the question wants us to say what functional groups are present. So you do need to pick out the different functional groups present. If we start with this OH here, now normally you'd think OHs are alcohols, but in this case it's not just any sort of aliphatic alcohol. It is an OH group attached to a benzene ring. Of course, that gives it quite different properties to an aliphatic alcohol. And of course, such an OH attached to a benzene ring is known as a phenol. Okay, so we've got a phenolic OH, or phenol. And then over on the other side of the molecule of paracetamol, we've got another functional group. And if we use a different color perhaps to highlight it, so we've got this functional group here, which on first inspection you might think, oh, that's an amine, but not quite, because the nitrogen is bonded to the carbon of a carbonyl group. Okay, so what we've got there is actually an amide bond. So a lot of students do get tripped up when amides are shown. So you've got the carbonyl C double bond O group, and that carbon of the carbonyl is bonded to a nitrogen. Okay, so that makes it an amide. So our second functional group is, of course, the amide. Okay, so another 2 marks hoovered up, hopefully, if you were doing this at the same time as I was doing it. Okay, so those are sort of the first 2 parts. If we look at the next part, so B part 2, and this time around we've got a 2-stage synthesis of paracetamol shown. And to start with, you've got your nitrophenol molecule, so 4-nitrophenol, and it undergoes a transformation, so stage 1, where we're going to be asked to say what the reagents are and conditions very shortly, to form an intermediate, which in turn goes on to react with your acyl chloride to give you paracetamol. Okay, so this is quite a big question and requires you to plan your answer quite carefully so that you don't miss out on any marks. So we're asked to describe a 2-stage synthesis of 5 grams of pure paracetamol. Okay, so 5 grams of pure paracetamol from 4-nitrophenol. The overall percentage yield, we're told, of paracetamol from 4-nitrophenol is 40%. Now, this is very important for the calculations that follow shortly. So, in your answer, we want to include the mass of 4-nitrophenol required. Okay, so that's something you need to highlight. We need to know what mass of 4-nitrophenol is going to give us the required amount of paracetamol being synthesized. We also need to include the reagents and intermediate. So that would be another part of your answer. And finally, we want to include details of the purification of paracetamol. Okay, so details of the purification of paracetamol would be a third part to your answer. Okay, so 3 things we need to take care of. Right, so let's start by tackling the question then. How do we work out the mass of 4-nitrophenol required? Okay, so we want to make 5 grams of paracetamol, right? And that represents 40% yield. So let's start by putting a heading for this part. So mass of 4-nitrophenol required. So that's the first part of the exercise or task. We know that 5 grams of paracetamol is 40% yield. 40% yield is equal to 5 grams of paracetamol. Okay, now notice how I am sort of labeling and annotating using lots of words so that I know exactly what the calculation or what part of the calculation I am tackling. And if I do make an error further down the line, it becomes very clear as I work through, as I troubleshoot where exactly I need to sort of fix things. So 40% is equal to 5 grams. A question to ask yourself is, well, what would 100% conversion be? So 100% conversion would be, so 100 times 5 over 40. Okay, so if the yield was 100%, it would be so 500 over 40. Trust your calculator. That would be 12.5 grams of paracetamol. Okay, so 12.5 grams of paracetamol. Now, the next thing to do, I guess, is to ask yourself, well, how many moles of that is equal to 12.5 grams of paracetamol? Okay, so moles of paracetamol. And again, note how I'm writing a lot. So N being the number of moles. And number of moles of paracetamol is equal to 12.5 grams. And we need to, at this stage, very quickly work out what the MR of paracetamol is. Okay, so I'm going to do this on my calculator very quickly. Hopefully, I won't make any errors. We've got we've got 2 oxygens, so I make that 32. Plus, we've got 1 nitrogen, so I'm going to add 14. And then we've got 1, 2, 3, 4, 5, 6. If I highlight this as I do it, we've got 1, 2, 3, 4, 5, 6 carbons, 7 carbons, 8 carbons. So that would be 8 times 12. Okay, and then we want to count all of the hydrogens. So for the hydrogens, I've got 1, 2, 3, 4, 5, and then I've got 6, and then I've got 7, 8, and 9. So 9 hydrogens altogether. Okay, so that's 151 is our MR for paracetamol. So if I divide 12.5 by 151, that gives me 0.0828 moles. Okay, so if I select my pen, so 0.0828 moles. Okay, so we've worked out the number of moles if we were going to get 100% yield of paracetamol. Okay, so now working backwards and using the reaction scheme shown us, where you've got your 4-nitrophenol going via an intermediate to the paracetamol, the molar ratio is still 1:1. So if you take 1 mole of 4-nitrophenol and convert that to paracetamol, you should expect, if everything goes perfectly with 100% yield, to get 1 mole of paracetamol as well. Okay, so if we now work backwards to to calculate the mass of, so let's write a statement about the molar ratio. So molar ratio of 4-nitrophenol to paracetamol is 1:1. Okay, so having done that, so we would expect to have 0.0828 moles of 4-nitrophenol. So we can work out the mass of 4-nitrophenol. And we know that the number of moles is equal to mass over MR, so the mass must be equal to the number of moles times the MR. So 0.0828 times the MR of 4-nitrophenol. So we need to go back to our scheme and again work out the MR. So if you've got 4-nitrophenol, again we've got, this time round we've got 3 oxygens in 4-nitrophenol. So if I use my highlighter again, there's one of them and there's another 2. So we've got 48, which is 16 times 3. So 48 plus 1 nitrogen, so 14, plus we've got, let's do the carbons. We've got 1, 2, 3, 4, 5, 6 carbons. So that's 6 by 12, which is 72. Okay, and then we've got to count the hydrogens as well. So the hydrogens, we've got 1 hydrogen there. We've got 2, 3, 4, 5, and yeah, that would be it. Plus 5 hydrogens, which should give us 139 as our mass, or MR or RFM of 4-nitrophenol. And if we then multiply that by the number of moles, so 0.0828, that should give us 11.5 grams. Okay, so that's quite a bit of work to do to get to the mass of your 4-nitrophenol required. Okay, so 11.5 grams, 40% yield would get you to the 5 grams of paracetamol required. Okay, so that's the first part of our answer. Now, the second part of our answer requires us to say what the reagents and the intermediate are. Okay, so what we can do is perhaps divide our answer page into, okay, it's a little box there, and look at the reaction going on in stage 1. And clearly, we want to make an amine eventually, because in stage 2, that amine is going to react with acyl chloride to give you the amide formed in paracetamol. Okay, so the intermediate has to be an amine. If we highlight this point, okay, so in stage 2, you've got this acyl chloride here, and that is being used to form an amide, okay? And so we need an amine as our intermediate. Our starting compound is 4-nitrophenol, it's got a nitro group. How can we convert that to an amine? So we can annotate this and say, convert to amine. Okay, and the way to do that is, of course, to reduce it. And to reduce that, we will need to react it with tin and concentrated hydrochloric acid. So in the second part, we want, I draw my 4-nitrophenol again, so NO2 and OH here, and that is being reacted with tin and concentrated HCl. Okay, so that would be your reagent combination to give you the amine. Okay, so reduction of our 4-nitrophenol to the amine. Okay, so if we highlight the key points required for the marks at this stage, it's the reagent, which is tin and concentrated hydrochloric acid, and the other mark would go for the amine product, the intermediate there. Okay, so We're almost there. We're almost at the end of the question. The final part asks for details of the purification of paracetamol. Okay, so paracetamol is an organic solid, and we're going to be purifying it. Okay, so purifying your organic solid, that's white and blue, purification. The first thing you want to think about is recrystallization. How do we carry out a recrystallization? If you simply write recrystallization down as the details of your purification, well, clearly that's not detailed enough. All you've done is given the name of the process. You want to show that you actually know how to carry out a recrystallization. So here's what you want to say. So you're going to dissolve paracetamol in the minimum amount, the minimum volume of hot solvent. Okay. So key things here, key pieces of detail are minimum volume and hot solvent. Okay, minimum volume because you don't want to add too much solvent so that when it cools down, you don't have a saturated solution and you don't get any crystals forming. Okay, so the minimum amount of hot solvent required. Obviously, if your solvent isn't hot, then you're not going to be able to dissolve your solid. If your solvent isn't hot and it dissolves your solid, then it's not a very good solvent for recrystallization because you're not going to get any crystals from it. Okay, so that's the first thing we want to do. We've dissolved our paracetamol in an amount of hot solvent. The next thing we want to do is to leave it to cool to room temperature. Leave to cool to room temperature to allow crystals to form. Okay, so we're going to leave it to cool down to room temperature. Now, crystals will probably start forming before it gets to room temperature. If you stop at that point to filter, you'll lose a lot of yield. Okay, so you want to cool it as far down to room temperature as possible, and so you can even scratch the insides of your flask to cause crystallization to happen if it isn't happening at room temperature. And then at this stage, you can then filter your solid. So filter or crystals using Buchner funnel. And suction, if you want, under reduced pressure. And then you want to wash your solid with cold solvent. So that gets rid of any soluble impurities. Okay, so wash crystals with cold solvent to get rid of, let's okay, so we've got rid of soluble impurities and we've washed it. And so the next thing to do is to dry it. Okay, so dry, so between 2 bits of filter paper or in a drying oven, you need to check that your solid is not going to decompose at the temperature you've set your drying oven to. Or you can simply just leave it to dry over a period of days. Okay, so quite a challenging question with a lot of effort going into getting all the marks. What we can do now is check the answers against the mark scheme. So if we look at the mark scheme for your unified paper, this is paper 4. There we go. Okay, so we did start with the oxidation number for platinum, which is +2. So we've got ourselves a mark there. We've got the correct curly arrows, so another 2 marks in our question. We move on to the functional groups. We've got phenol and amide, which is excellent. And then if we look at the big chunky 6 marker, it says to get level 3, which is 5 to 6 marks, so there's a correct calculation of the mass of 4-nitrophenol. So we check our answer against what is obtained here. There we go, 11.5 grams. So that's so we're on our way to getting full marks. It identifies the reagents and intermediates. So reagents and intermediates would be, there we go. So tin and concentrated hydrochloric acid. Intermediate is 4-aminophenol or structure. Okay, so we've got that as well. And then in the final part, there's a detailed description of most purification steps. Okay, so don't have to be 100% perfect there. There's most purification steps. So if we look at the detail, it says dissolve your impure solid in minimum volume of hot solvent, cool the solution and filter solid, which we talked about. We did mention scratching with a glass rod, although I don't recall us writing it down, and then washing with cold solvent and drying. Okay, so we've pretty much got every single mark or marking point there, and so that should sort of obviously score us 6 marks. So I think that's a pretty good effort on our part. Okay, right, so at this stage I'm very quickly going to check to see if there are any questions in my chat box. I can't see any at the minute, so we'll carry on with the next question, which is question 5. Okay, so if we move on to question 5, there we go. Okay, so in question 5, we're told the student carries out 2 experiments in the lab based on succinic acid. The succinic acid is butane dioic acid, and it's always a good idea to, I think it's always a good idea to draw to the skeletal formula or display formula. Even at this stage, you should be pretty practiced at drawing skeletal formulae. But butane dioic acid, if I do this in blue, so we've got a carboxylic acid group at one end. That's 2, 3, 4. There we go. There's the other end. Okay, so that's the dicarboxylic acid we're looking at, succinic acid or butane dioic acid. So aqueous succinic acid can be neutralized by aqueous sodium hydroxide, so NaOH, and you've got a balanced equation given to you. So pay attention to the molar ratios here. You're probably going to be needing it at some point. Okay, so this reaction can be used to determine a value for the enthalpy of neutralization. The student follows the method shown. At this stage, it's important to think about what the definition of neutralization, the change in neutralization enthalpy is. Okay, I wouldn't tell you what it is just yet, but it will be very relevant in this question. So the student follows this method, right? At 50 centimeters cubed of 0.4 mole per decimeter cubed succinic acid per polystyrene cup. Okay, so that immediately allows us to work out the moles of our succinic acid. Okay, so highlighted in yellow there. It says measure out 50 centimeters cubed of 1 mole per decimeter cubed sodium hydroxide, which is in excess. Okay, so we don't have to worry about the moles of sodium hydroxide, but if you wanted to, you could calculate it as well. Measure the temperature of both solutions, add your sodium hydroxide to the aqueous succinic acid in a polystyrene cup, stir the mixture and record the maximum temperature. Okay, so the temperature readings are given to us in a table. And in the next part of the question, we're asked to calculate a value for the enthalpy change of neutralization in kilojoules per mole. Okay, so very important to highlight what we're trying to do in this question. Work out the change in neutralization enthalpy in kilojoules per mole. Assume that the density of all solutions and the specific heat capacity C of the reaction mixture are the same as that for water. Okay, so some important assumptions there. And we can always look up C in our data sheet. If you can't remember it, use 4.18. There we go. So that's C, 4.18. Okay, so back to our question then. First thing we want to do is work out the moles of our succinic acid, right? So easy place to start. Moles of succinic acid. And that would be, so if we think that concentration is the number of moles divided by volume in dm cubed, then the moles of the volume will be the volume in dm cubed times the concentration. Okay, so 50 over 1,000 is the volume in dm cubed times the concentration, which is 0.4. And that gives us, we work this out, so 0.05 times 0.4 give us 0.02, yep, so 0.02 moles. Okay, so that's definitely worth a mark, working out the number of moles. Okay, now, the next thing we want to do is to work out what the heat energy change is. Okay, so at this point, we want to recall the equation Q, which is the heat energy change, equals mc delta T. Okay, now as soon as you've written that equation down, automatically your brain goes, right, what is delta T? Can we calculate it? That's where you go back to the table to look at the data given. So for delta T, we've got 26.5 minus 21.5. Okay, so let's do that here. Delta T is equal to 26.5 minus 21.5, and even I can do that without my calculator. So we've got 5.0 as our change in temperature. Okay, 5.0 degrees C. Right, so let's work out what Q is then. Right, M in mc delta T is the mass of our solution. Okay, so we take 50 centimeters cubed of one solution, succinic acid, and we add 50 centimeters cubed of another solution. So we've got a total of 100 centimeters cubed, and so the mass of our solution is 100 grams. Okay, so M is equal to 50 plus 50, and so we've got 100 grams times C, which is 4.18, and we've got delta T, which is 5. Okay, so we do that very quickly. We've got 500 times 4.18. Okay, yeah, just over 2,000, so 2,090 and 90 joules. Okay, so that's in joules because our units of C has a joule term in it. If you don't believe me, you can go back there and you'll see that C is joules per gram per Kelvin. Okay, so 2090 joules. And then the next part of the question requires us to work out what delta H is. Okay, so this would be delta H for the reaction. Okay, so remember the reaction is between succinic acid and sodium hydroxide. Delta H is going to be our Q over the number of moles we worked out earlier. So delta H being Q over N, ourselves, 0.02. If we do that, so 2090 divided by 0.02 gives us 104,500 joules per mole. Okay, now you might think, right, we simply need to divide by 1,000 at this stage and we're done. We've got our answer in kilojoules per mole. Okay, now you do need to do that, but that's not quite all of it. Okay, I'll point out why in a second. So if we divide answer by, so in kilojoules per mole would be what, 104.5 kilojoules per mole. Okay, but we're not quite done yet, because if we go back to our equation and we look at succinic acid, I'm going to highlight it here, and perhaps let's use yellow. Okay, so we highlight the formula for succinic acid, and more importantly, the structure for succinic acid. You should be able to immediately see that each mole of succinic acid we've got is capable of releasing or donating 2 moles of protons. Okay, so 2 moles of protons, it is diprotic, which is very important. Let's annotate this. So this is diprotic. Now, the enthalpy change of neutralization is referring specifically to 1 mole of H plus ions being neutralized. But our succinic acid is producing 2 moles of H plus ions for each mole of succinic acid. And so we need to divide our answer by 2 to get the neutralization enthalpy when 1 mole of H plus is neutralized. Okay, so back to our answer there, we need to divide that by 2. So we can annotate this here. So if we do this in black, divide by 2 because succinic acid is diprotic. Okay, so once you've spotted that, you aren't going to throw away that final mark. So we divide by 2, we should get 52.25 as our answer. We could round it up to 3 significant figures, so 52.3 kilojoules per mole. Okay, so another tough question to tackle, but if you've got your wits about you, if you're careful in underlining everything that is relevant to answering the question or highlighting it, and also linking back everything you do to definitions you've seen before. Okay, so knowing your definitions accurately would allow you to work out that because you've got a diprotic acid with 2 moles of H plus ions, you would need to divide it by 2. Okay, so sorry, I've just seen your question. So the question is, how do you know it is diprotic? Hopefully it is answered for you. But if it isn't clear, going back to the structure, so I'll redraw the structure here to show you why it is diprotic. So we've got C double bond O, OH, and 1, 2, 3, 4. Here's our other C double bond OH here. Now, if we compare our succinic acid to, say, ethanoic acid, which is another carboxylic acid. So here's ethanoic acid. For all carboxylic acids, the protons that are donated are the ones I'm going to highlight here. So for ethanoic acid, this proton here that is bonded to, single bonded to the oxygen, so your OH proton, that is the acidic proton. Okay, so if we label that, so this is the acidic proton. So for all carboxylic acids, so C double bond OH, okay, so whatever R is, this is the acidic proton. Yeah, so if ethanoic acid has only got 1 proton to give away, it is, of course, monoprotic. If you've got a dicarboxylic acid, so in the case of succinic acid, you've got this proton here, and you've got that proton here. So if you draw out the structure, which is why I drew out the structure at the very beginning, that allows you to see that it is diprotic. Hopefully that is clear enough, but do ask a follow-up question if it isn't, and if it is clear, do give me a thumbs up or some I guess some signal to say that you've understood it. Okay, so that is, thank you very much. Okay, so that is our, so I've lost track of which question we're on. So yeah, question 5 and 5A. So if we move on to the next part of question 5, so this is part B, we're still looking at succinic acid, but this time round in a different context. So we're going to be looking at equilibrium. Okay, so we're told it is esterified using ethanol in the presence of an acid catalyst to form an equilibrium mixture, and the equilibrium constant Kc is given by the expression shown there. The first thing you'll notice about this expression here, and I'll highlight things again, is that it's not in the usual form. Usually we express Kc in terms of equilibrium concentrations, but here we're being told to think in terms of the moles of the different substances at equilibrium. So you've got moles of your ester times moles of your water molecule to the power 2, and below that you've got moles of your succinic acid times moles of your ethanol to the power 2. Okay, so in a different form, which we will sort of need to be sort of wary of. Right, so a student carries out the experiment to determine the value of Kc for this equilibrium. The student mixes together 0.05 moles of succinic acid with your ethanol and adds a small amount of acid catalyst. The mixture is allowed to reach equilibrium, and then the student determines that 0.02 moles of succinic acid are present or left over at equilibrium, another way of thinking about it, are present in the equilibrium mixture. So we'll come back and highlight some important points very shortly to do with the experiment itself. The first question to address is which technique could be used to determine the equilibrium amount of succinic acid? If you want to know how much acid there is present in a solution, what do? You'll carry out some sort of titration. Okay, so an acid-based titration is what would be required here. So straightforward enough. In the second part, we're asked to write the equation for the equilibrium reaction that takes place. Okay, so we've got succinic acid to begin with. Okay, so the formula of succinic acid is CH2, COOH. You can draw this as a skeletal formula if that, and that is usually what I do. It's even quicker, but I'm mindful that we've got the formula given to us, so I'm just using that. Okay, so that's your succinic acid, and we're reacting it with ethanol. And if you pay attention to the powers of the terms in your expression, that is indicating the number of moles. So you don't have to think too hard about balancing your equation. So we've got ethanol, which is C2H5OH. Okay, and if we think about the powers, we're going to have 2 moles of that. And then our products, we've got your CH2, C double bond O, O, C2H5, so that's your ester, or your diester, I should say. And yep, so that is your, there we go, 2. And we're going to have water on this side, and we're going to have, again, 2 moles of water. Okay, so that's our balanced equation, and all I did was look at my expression for Kc and to sort of use that to write my balanced equation. And then you can, of course, double check that everything is balanced in terms of carbons and hydrogens and oxygens if you wish to. Okay, so we're asked to draw the skeletal formula of the ester present in the equilibrium mixture. So I drew the skeletal formula for succinic acid earlier, so it's just building on that. So if we start by showing the carbonyls at either end, okay, and then we're making an ester. Just check that you've got the right number of carbon atoms. So you've got 1, 2, 3, 4. There we go, so all sorted. And we're forming an ester with ethanol, so it's going to be an ethyl ester. Okay, so there's your skeletal formula for the ester present at equilibrium. Right, so part 4 then. It says write an expression, oh, sorry, why can expression 5.1, so let's remind ourselves what expression 5.1 is. I'll tidy it up a bit, get rid of my highlighting. So that is, I choose a different color to highlight it. Yeah, that should be fine. So there's our expression there. And we're asked why we can use that instead of using the equilibrium concentrations. Okay, so the answer is it's fairly straightforward. Okay, so if we looked at the expression again, you've got the moles of the ester times the square of the moles of water. You can write that as N brackets H2O times N brackets H2O. Okay, so we're squaring the water term. And then below that, you've got your moles of your succinic acid, so NCH2C double bond OH brackets 2, times the moles of your alcohol, your ethanol square. Okay, so it'd be NC2H5OH times NC2H5OH. And as soon as you do that, you realize that if you were to find the concentrations, you'd be dividing all of those terms by the same volume. So the volumes would cancel out in all instances, and the ratio of the top terms over the bottom terms should remain the same. Okay, so it's simply because the volumes are going to cancel out. So the volumes will cancel out. So if you work out the concentrations, you'd be essentially doing an unnecessary step because the ratio would end up being the same because you're dividing each of those terms by the same volume. Okay, so volumes will cancel out. Okay, so hopefully that is clear. If it isn't, do ask me and I will sort of break it down even simpler for you. Okay, right. Calculate the value of Kc for this reaction and show your working. Okay, so we've got an expression for Kc which we're required to use. Before we can do that though, we need to work out what the equilibrium quantities are. Okay, so the first thing I would do is rewrite the equation again. I have this sort of foolproof method for doing these sorts of calculations, and if you are consistently using it, then you're less likely to make silly errors. Okay, so I'm going to rewrite the equation. So we've got our succinic acid, which is CH2COOH, got 2 lots of it. And then you've got 2 moles of our C2H5OH. And we've got our ester, which is CH2COO, C2H5, brackets, little 2, and 2H2O. Okay, so write that down, and then underneath it, write down starting moles. Okay, so starting moles or initial moles, whatever you want to call it. And then if we go back to the data we've been given, okay, so the student mixes together 0.05 moles of succinic acid. Okay, so 0.05 and 0.15. So let's highlight this to make it clear where the numbers are coming from. So that's succinic acid and 0.15 moles of ethanol. Okay, so 0.15 moles. So write that underneath correct sort of formula. And we've got 0 ester and 0 water at the beginning. Okay, the student mixes together the 2 reactants. There are no products at the beginning, so 0 moles of products. Okay, and then at equilibrium, so next line, write down equilibrium moles, EQM for short, EQM moles. And what are we told? At equilibrium, the student determines that there are 0.02 moles of succinic acid. Okay, so that's really useful information, 0.02. Okay, so that's how much of succinic acid we've got left at equilibrium. Now, if you look at the molar ratio of succinic acid to ester, it is 1 to 1. Okay, hopefully you can see 1 mole of succinic acid gives you 1 mole of ester. Now, if we've got 0.02 moles of succinic acid left, having started with 0.05, that is telling me that I've got 0.03 moles of succinic acid, can't get that word out. I've used up 0.03 moles of succinic acid. So 0.05 minus 0. Take away from that 0.02 should give you 0.03 moles of your acid used up. And if you use up that number of moles of acid, 0.03, you should expect to make 0.03 moles of the ester. Okay, so we put 0.03 here. Okay, now for every mole of the ester you make, you're going to be making 2 moles of water. Okay, so how do I know that? I'm now comparing this with that, and the molar ratio there is 1 to 2. So if I've made 0.03 moles of ester, I would expect to make 0.06 moles of water. Okay, now the trickier equilibrium quantity to work out is the ethanol. Okay, so we know that we've used up 0.03 moles of acid, but that 0.03 moles of acid reacts with double that number of moles of ethanol. Okay, so 0.03 times 2 is 0.06 moles of ethanol that's going to be reacting. So if we want to know how much ethanol is left at equilibrium, we need to do 0.15 take away 0.03 times 2. Okay, and that should give us, if I do that quickly, so 0.15 minus 0.06, which is 0.09. Okay, so we've now got all of our equilibrium quantities sorted. We can now use the expression. Okay, so the expression says moles of our ester at equilibrium, so 0.03 times moles of our water to the power 2, 0.06 to the power 2, divided by moles of our acid, which is 0.02, and multiply that by 0.09 to the power 2. And if you do all of that accurately, you should have worked this out to be 0.667 as your final answer. Okay, so again, you've got to be very sort of methodical, make sure that you're sort of taking into account all the information you've been given. And a good way to do that for these sorts of calculations is to have a system that you always follow. So in this case, write down the equation, write down the starting moles, and then a second line below that to work out the equilibrium number of moles. Once you've done that, it then becomes a straightforward case of plugging in the numbers, and then you should get to the correct answer. Okay, so at this stage, a very quick check to see if there are any questions. There aren't, so I will carry on. So, okay, so that was the end of question 5. Let's have a look at the mark scheme to see how we've done. If we go back to the mark scheme and to our calculation, so succinic acid and the fact that it is diprotic, so that's what we were looking at earlier, so 52.3, make sure you divide 104.5 by 2, and then we talked about titrations, so that was good. Balanced equation, correct number of moles, it's very good. There's our skeletal formula shown, there we go, and then why we can use the Kc expression where we're using number of moles rather than equilibrium concentrations, because you've got volumes cancelling out, you've got the same number of terms at the top as you've got at the bottom, so you should get the same ratio. Final answer, 0.667 for Kc, and brilliant. So we can move on to the final question then. So if we look at the final question, and let's make this a bit larger. So there we go. Hopefully you've got you can all see it clearly. Question 6 looks at an organic reaction this time around. So compound A is formed when ethanol, which is an aldehyde, is mixed with OH minus ion. So we've got some hydroxide ions which act as a catalyst. And the balanced equation is shown, you've got 2 ethanol molecules coming together to give you the final compound, which we're asked for the systematic name for. So functional groups we need to consider is that one there, which is the CHO, so that's an aldehyde. And the aldehyde functional group is more important than the OH functional group. It's at a higher oxidation level. So this is going to be an aldehyde. And so I've just seen another question. So this question says, well, would there be any marks for units in the question? Presumably you're referring to if we go back to our calculation. In this question, there are no units. Why? Because all of the terms would cancel out. So firstly, we're using an expression which looks at moles, right? And moles has got no units. It's just sort of quantity or amount of substance. But also, even if you worked out the Kc value using the concentrations, all of the concentration terms will cancel out. So all of the units of concentration would cancel out, and there would be no units as a result. Okay, again, so good. So yeah, you've acknowledged that. Very good. So we can move back to our organic question. And if we look at the naming of compound A, it's an aldehyde rather than an alcohol. Aldehydes are more important. So this would be 1, 2, 3, 4. So it is butanal, but it is substituted. It's got an OH group at position number 3. So if we number this, this would be carbon number 1, that would be number 2, and that would be 3, and that would be 4. Okay, so I always write my names from the right-hand side. So from the parent names, I've got butanal, and it is 3-hydroxy. So hydroxy, and the hydroxy group is at position number 3. Okay, 3-hydroxybutanal. Right. And I've got another question about counting carbons from the other way. You can only sort of count carbons from the other way if, in this case, your aldehyde is on the other side. So you want to give your parent name and the aldehyde functional group as low a number as possible. Okay, so rather than well, I get it for the aldehyde, because it's always at the end, and it's in this case the most important functional group. That's what's going to determine the numbering system. So in this example, no, you can't count from the other side. Okay. If we didn't have an aldehyde at the end, and you just had a carbon atom, so if it was just the alcohol, then it would be a case of either being butan 2-ol or butan 3-ol. But of course, we always want to give the lowest number possible. So in that instance, it would be butan 2-ol. Okay, so hopefully that clears up that question for you. If it doesn't, I will come back to it. Right, so you've got 3-hydroxybutanal, and because you've got an aldehyde, which is always at the end of the molecule, and in this case, it's the most important group, that's always going to determine the numbering. So that carbon with the OH group on it will always be number 3, because it's the third carbon from your aldehyde. Okay, so counting the aldehyde carbon, of course. So what type of reaction has taken place? You've got two things coming together to give you one molecule. There are no other products, so this is an addition reaction. Okay, so addition would be the answer, no other products formed. And in part 3, we're asked to look at or complete the equation to show what the conjugate acid-base pairs are. So in step 1, ethanol reacts with OH minus ions to set up an acid-base equilibrium. So if we complete that, so your OH minus ions are going to be removing a proton from your aldehyde. And so if we did that, you would have or end up with CH2 and CHO. Okay, and you would end up with a water molecule. So COH. Let's draw this, because it's always easier to show this as the skeletal formula. So you would end up with this species here. Okay, so that's your what is often referred to as an enolate. You don't need to worry about the name for it. That's what's going to happen. And if we therefore write the structural formula for it, perhaps let's just move that out of the way. Let's move that to there for a second. And so that would allow us to work out you've got CH. So we've got CH2, CHO minus. Okay, so that's our structural formula. You've also got the skeletal formula to the left-hand side for you. And you'd also be making water as a byproduct. Okay, so in terms of our acid, so A1, we've got the aldehyde donating its proton, and the A2 would be over on the other side, which would be water acting as an acid. So that would be A2, and that of course means that we've got B2 on this side, and we've got A1 on that, sorry, A2 I should say. Let's get rid of that, and A2 on this side. Okay, so we've got our equation completed, and we've identified the acid base pairs. Suggest the equation for step 2. Okay, so in step 2, we've got our CH2. So I'm going to show it as a skeletal formula again. So if I use a highlighter to indicate what's going on here. So that here. And I will answer your question very shortly about B1 in a second. So we've got that, we've got this here having to react with another aldehyde molecule. So it would be that aldehyde there. And of course, it would need to react with water as well, so that you've got product being formed, and product being formed is, of course, we go back up to the structure. You've got the aldehyde, and then you've got the OH there, and then you've got the CH3 at the end, plus an OH minus. Okay, so I've got a question about the CH2 CHO minus being B1. You could, it could be B1, which would of course make the, you're absolutely right, sorry, I've seen what you mean. Thanks for pointing out that error for me. So I've got A1, and so that should be B1, you're absolutely right, that's my fault. There we go, so B1. Sorry about that. Sorry for giving you a heart attack. So yeah, so you've got your the acid base pairs correctly shown now. So on the left hand side, you've got the aldehyde, which is your acid, and its counterpart on the left hand side. So your B2 is your hydroxide ion, and then over on the other side, the acid on the right hand side, the acid would be your water molecules. So that would be A2, and the base would be B1, would be your CH2 CHO minus. Okay, brilliant. So can you write equation 2 with structural formula? So equation for step 2. Yes, you can. You absolutely can, and I can do that for you. So we could simply go CH2 CHO minus plus our aldehyde, which is CH3 CHO plus water, and that gives us the product. So that would be CH3 CHOH CH2 and CHO plus OH minus. Okay, so both are fine. I do have a I do like working using skeletal formulae because I find I write a lot faster. But certainly you can write structural formulae if that's what you're more comfortable with. Okay, so hopefully that's all clear for part 3 of that question. Part 4, we're told a similar reaction takes place when propanone is mixed with hydroxide, aqueous hydroxide. So propanone is this molecule here, okay, and that's going to react with another molecule of propanone, we're told, okay, and we want the structure of the organic product formed. So if we again think about what's happening in the first instance, we're going to form, there we go, an OH there, and you're going to have that there, and we're also going to have a methyl group there. Okay, so the answer, if I highlight this for you, is going to be that structure there. Okay, so this is simply copying what has happened with our aldehyde and applying it to propanone. Okay, so OH minus as our catalyst. So okay, so the question is, why are two propanones reacting? This is a similar reaction takes place when propanone is mixed with OH minus ions. Well, if you go back to the original equation, you've got two molecules of aldehyde. It's an addition reaction, remember? So you need two things to come together to give you your product. So if you've got ethanol as your the reagent in your flask, then you're going to add two ethanol molecules together. If you have a similar reaction using propanone instead, then all the molecules in your flask are propanone, and you'll get two molecules of propanone coming together in the same way. Okay, so hopefully that's cleared things up for you. And then very quickly, so we've got a big question here that I can answer this in bullet points and perhaps show you how you can do the same if you're running out of time in an exam. Okay, so many organic reactions use electrophiles as reagents. If I highlight electrophiles here, key term, explaining the role of electrophiles in organic chemistry. So explaining the role of electrophiles in organic chemistry is what we're going to be doing for the most part in this question. Your answer should include one reaction of an aliphatic compound and one reaction of an aromatic compound. So we want one reaction of an aliphatic compound and we want one reaction of an aromatic compound. And we must include relevant mechanisms. Okay, so we can break this down into maybe 3, maybe 4 parts. The first thing I think we should do, and it'll definitely be worth some credit, is saying what an electrophile is. Okay, so an electrophile is defined as an electron pair acceptor. So that must be in your answer. Okay, so in explaining the role of electrophiles in organic chemistry, you want to show that you know some examples of electrophiles and reactions involving electrophiles. Okay, so we can think of so electrophilic addition, for instance. Okay, so we can start with electrophilic addition, and naming this mechanism will again give you some credit. Okay, so electrophilic addition, and if we take an example, say ethene reacting with hydrogen bromide, so HBr. Okay, we can show, so this is the overall equation. You end up with bromoethane. Okay, so we've added HBr across the double bond. How does it happen? You've got HBr, which is polar, so you've got delta plus here and a delta minus there, curly arrow to your hydrogen, and then breaking the HBr bond, and that gives you an intermediate, which of course is a carbocation. So carbocation plus Br minus, and in the final step, you've got your Br minus. If we get rid of the plus here, it makes things a little bit clearer. And so your Br minus attacks your carbocation and gives us our final product. Okay, and in this case, HBr is our electrophile. HBr is electrophile. Okay, so that's sort of pretty much 2/3 of our question answered. We can also give an example involving an aromatic compound. So, for instance, we can look at nitration of benzene. Look at let's do it in a different color. Nitration of benzene. And in that, you need to produce your NO2 plus electrophile. How do we do that? We need nitric acid and sulfuric acid. And initially, you're going to end up forming H2NO3 plus. plus HSO4 minus, and then your H2NO3 plus will break down. Will give you your NO2 plus and water. Okay. Okay, so you will get credit for knowing how this electrophile is formed. Okay, so NO2 plus, and then of course there's more marks to be gained by showing the mechanism. So if we label this as our electrophile again, electrophile, and then in our mechanism we can show, we've got more room here so we can use the space. We've got benzene reacting with your NO2 plus, so curly arrow from the pi system of benzene attacking your NO2 plus. And then in your intermediate, you need to show the aromaticity having been disrupted, so plus charge and hydrogen and NO2. And then final step, reforming your aromatic pi system and NO2 as your new substituent, and of course H plus as your byproduct. Okay, so that is so a very quick run through of this question. We've defined what an electrophile is. We've looked at how it accepts an electron pair in two different examples. We've looked at electrophilic addition of HBr in this example with the mechanism shown, and we've also looked at the nitration of benzene, where we've shown the production of the electrophile and then shown the mechanism. Okay, so if we look at our mark scheme just to make sure we've covered every point that needs covering, so this is question 6. Going back to our answers, 3-hydroxybutanol was something we got right earlier. We've got an addition reaction, and I was very sort of quite rightly corrected on my labeling. There we go. So we've got B2 and B1, or if you want to go the other way, so B1 and B2 and A2 and A1 swapping sides. So all good as far as we can see. And then the equation for step 2, so your aldehyde and your enolate and your water coming together to give you the final product, which we wrote an equation for. And then if we move on to the next part, you've got the product where you've got two propanones coming together to give you that product there. Okay, and then finally for part B, the leveled marking question, 6 marks, says 5 to 6 marks, describes in detail and or in detail electrophilic reactions and mechanisms of one aliphatic and one aromatic compound. So we've described in detail, so we've got mechanisms down, and explanation of the role of electrophiles in organic chemistry. So suitable reactions, so we've chosen ethene and HBr, which we showed a mechanism for, and so we'd get all the marks there. Reaction of aromatic compound, we chose benzene and the NO2 plus from nitric acid, so we'd get all the marks there. We've got the mechanism as well, which we've got here. So that's our mechanism there. Electrophile as an electron pair acceptor, we said that. The types and names of the mechanisms, we did that as well. Equations for generation of the electrophile and regeneration of the catalyst. So we didn't talk about regenerating the catalyst. It might be the only thing we missed out on. Accurately positioned and directed curly arrows, charges and dipoles, which we did. And explanation of major and minor product from electrophilic. So that's something we didn't consider. Okay, so 2 things that you might want to add to this final answer. Obviously, we chose a symmetrical alkene, so we chose ethene, so there was no case of major and minor products being formed. But if you were to use, if I show this in red, if you were to use a different alkene, such as propene, then you would need to consider the position of the bromine when you add it. So whether you add it to the secondary carbocation or the primary carbocation. So that could be something else to think about. So hopefully all that is fairly clear, fairly straightforward. It's been a pleasure to go through this session. Obviously, we did so in quite some detail, but no doubt there may be one or two lingering questions for anyone watching this sort of later on. If you do have any questions, do get in touch with us at boostrevision.com, and we will be more than happy to write back to you with answers or to clarify points that we've made. As usual, it's been a pleasure to host you this afternoon, and hopefully I will see you again over the course of next week and certainly next weekend. Thank you very much for joining.